Hello ladies and gentlemen for another episode of Tailored Motor TV. This time we again make an autopsy of a motor, but this time a much more interesting motor than the last one, which was a standard induction motor. Now this time we have what some call a brushless DC motor or a permanent magnet synchronous motor, depending how you call it, with quite a high power density from one of the, in my opinion, leading manufacturers of compact brushless motors, Maxon Motors, Swiss company. And I got this one from some people who are making an exoskeleton. It was somehow broken, and so we can make an autopsy out of it for zero cost and have a look inside how exactly it was built. It is an outrunner motor, and let's dive into the details. So this is basically how it looks from the outside. We see here Maxon EC motor, EC for electronically commutated, which is another wording for brushless DC, with some model number. Then they say also it's assembled in Korea. So this is not one of the Swiss-made motors, but that's an imported one. Now I was looking for the data sheet. In the background you see a data sheet. I was looking for the data sheet of this model number. Unfortunately, this model number doesn't exist anymore, online at least. So it's just a guess that the data sheet matches the motor. Unfortunately, that's also something we at Tailored Motor would never do. If you have a type of motor out in the wild, you must provide the according data sheet in the future, so it is always traceable what kind of motor you have if you just find it somewhere in your company or in your lab. Now inside the motor there's nothing. Why? Because I've already taken it apart. So that's how it looks from the inside. And I have counted the coils. We have 18 coils. Of course, it must be a number divisible by 3. So originally the whole thing looked like this. We had the bell on top with the magnet here inside. Then in the middle we have a shaft with 2 bearings. That helps everything rotate. And then we have this stator, which was press fitted here on the aluminium backplate. And the stator, as we see, the stator is directly mounted on a PCB. On that PCB we see 1, 2, 3 Hall sensors for the feedback, and we have here another sensor that is for the encoder. On the back of the bell we see that there is a PCB with little stripes on it that's glued on, so we can remove it. And I'm not 100% sure how this encoder is gonna work, if it uses the conductivity of the copper or if it just uses the contrast between copper and PCB. So I'm not sure if it's optical or electromagnetical, but this ring flies over this sensor, which gives us then an RPM feedback, which probably about 500 to 1000 increments per rotation. Now what's quite interesting if I look at this motor design, first obvious thing is we have plenty of air here in, so we could fit a lot more copper on these coils. So either we make more turns or we take a thicker wire. If we make more turns we get more magnetic field per flowing current. If we make a thicker wire, we have less ohmic losses for the same current, or we can push more current through, getting a better magnetic field for the same ohmic losses. So, in my opinion, this is far from optimal. We could improve the power density even more. I mean, the power density is quite decent. I mean, that's compared to the size of my hand. Okay, I don't have the smallest hands, but it's quite a small motor with a nominal power of 90 watts. So it's okay. But still, if you want to make a high power density motor, you want to fill these coils with more copper. So that's one thing. Then the second thing is the conductivity, the thermal conductivity. You are going to generate losses on this stator. You have these ohmic losses, you have also a little bit of eddy current losses. All this is going to generate some heat, and the only way to get the heat out is this backplate. This backplate is screwed somewhere, is aluminium, is a very good thermal conductor. Now, what's the only contact we have between the stator and the backplate? It's these 3 points. You have only these 3 points as a contact to drain the waste heat we're generating. We don't go directly down to the plate from the single poles, because we have the epoxy in between, and epoxy is quite a good thermal insulator. So that's also one thing that will restrict our power density, is the cooling, because most motors die thermal death. So that's also something I would make in another way. So if someone from Axon is watching this, I don't want to offend anyone, maybe I'm completely wrong, but these are just some basic physics principles that I don't understand if I look at this motor design. One is how exactly you want to cool it, and how you get, why is not more copper inside. Because once you have this bell over it, it is completely closed, that motor, so it's difficult to drain the heat out. You can't push air through, how it's done with some motors. So these little coils will be kind of insulated and therefore hard to cool. If we look at the bell, at the rotor, the outrunning rotor we had, as I said, we had this encoder ring on it. We remove it and we look at the magnet. Now it's a magnet ring that is magnetized with different poles. Actually, it's a good trick to find out how many poles you have on a motor. I have here a little screw, and if I push it, you see it jumps. It jumps from here to here, and it jumps from one increment to the next. So here we have one magnetic pole, and the other one is probably about here. And in between we have the change, so maybe if this is north, this will be south again, and then again north and south and so on. And what I see is that we have quite a dark magnet, and in the first view, for me, this looks like a ferrite magnet, not like a neodymium magnet. So I wanted to be sure, and I have to correct myself. It is neodymium. It is a high power magnet. I broke it a little bit here, and we see quite a clear crystal structure. And if you have ferrite magnets that are much darker. This one, for example, is a ferrite magnet. You see that it's much darker, and so I'm pretty sure it is a high power magnet compared to that, which is, this one is a low power ferrite magnet. So we have here a neodymium magnet. with some black coating, whatever it is. Neodymium magnets are very sensitive to oxidation. You have to be very careful. If you don't protect them, they start oxidizing, and that then they get out of shape. So obviously that black paint on top of it is some corrosion protection. So we have a neodymium magnet ring, 24 poles, and we have over here the 18 poles of the magnet. So now let's have a closer look at that PCB which is underneath that motor holding everything together. Here we have 3 solder points which I had to rip off that go to these 3 wires. That's the Y connection point of the motor where the 3 coils are connected together. And these 3 are the 3 ends where you come in from the driver that are linked up to the main connector over there. Here we have Hall sensor 1, 2 and 3. Obviously with some little resistors and capacitors beneath it in order to have a better signal quality. And this leads over here to a little chip that is probably the driver chip to get a Hall sensor output. And over here we have the encoder chip that reads from that ring, as I said before. And then there is also an IC that helps convert that 1-0 data to a more useful encoder signal for the motor. Now, as I said, I'm not exactly sure if this is the right data sheet for that motor. However, it says 90 watts, 90 millimeters of diameter. 90 millimeters of diameter are correct. This is something I could measure. All other measures are also correct. It is sold on the website for 213 Swiss francs for 1 unit, and goes down as you buy more of them. So that's a pretty fair price for such a motor. I think that's probably one of the most affordable Maxon motors. Most other motors are way more expensive, probably also due to the fact that it is made in Korea. And I will also give you a closer look on that data sheet, because probably it is very close to the motor that we have here. But as you see, the numbers up here, 429, and these part numbers don't correspond to this, because here we have a 464 and you can't find a 464 motor on the Maxon website. However, let's have a look at what Emitor says to the configurations. Looking at what Emitor has to say about this configuration of 24 poles and 18 slots, we get a winding factor of 0.866 and the least common multiple between poles and slots of 72. Now, a winding factor tells us how many of the coils are helping to generate torque. Maximum winding factor, maximum possible, is 1, but is very rarely reached, and that means that all your coils are helping you produce torque. And the least common multiple of 72 tells us that we won't get too much torque ripple, because the closer the number of slots and poles are to each other, the more you get ripple in the torque because of the cogging. So if your magnet passes by a pole, it will be attracted and pushed away again, and so you feel that, like that cogging if you turn a motor by hand, assuming that you have a slotted motor. With slotless motors or with induction motors you don't have that cogging, but that cogging is one of the common problems you have with permanent magnet motors. And so the higher your least common multiple between poles and slot is, the higher these numbers get, the less you will get cogging torque. So this motor with 72 is quite good compared to a 1012 motor, which is a far more common design. Lots of brushless motors in RC cars and planes and stuff. Most drone motors have a 1012 configurations, which means 10 magnets with 12 slots. If you go to 10 magnets, 12 slots, you have a least common multiple of 60, and therefore you have a bit more cogging than with this motor. But if you have a 1012 motor, you have a much higher winding factor. You have a winding factor going up 0.9 something, so you also have a more efficient motor for generating torque. So that's always the compromise you have to find in motor design, is to have a right pole and slot combination in order to have a smooth running motor and still enough torque and a good efficiency. Obviously the guys at Maxon now had more the focus on a smooth run than on a high efficiency, so they had a little compromise on the winding factor, but a better least common multiple to have a smooth run. Feel free to go to Emitor. It's a great website to learn about motors, and you can try out many different configurations just like that, and so without having to build motors, already learn a lot. So that was looking inside a brushless DC motor, an outrunner, and especially one from a very well-known high-quality manufacturer. I hope I can get soon more motors to rip apart and show you inside and tell you what were the design considerations and so on. Thank you for watching. Don't forget to subscribe, and see you later. Bye bye.